talk about a very popular method for fatigue design, and the method is called the stress life method. In many situations, we also know the method by its popular name, the SN method. And in here, I'm going to describe first the relationship between the applied stress amplitude and the number of cycles to failure. So we'll try to focus on that as how we can construct this relationship. So let's consider first the way that the stress versus time look like in the simplest possible way. And the simplest possible way is fully reversed stress amplitude, and it looks like this, fully reversed, where we have on one side we have S, and on this side actually not S in this case, to be consistent, this is the applied stress and this is the time. Now we have a few things to think about. The distance between the amplitude of this stress wave, this amplitude here, we're going to call it S. So this is the amplitude, and this amplitude is a characteristic of the fully reversed fatigue test by rotating beam, as we mentioned before. Now, if we just keep applying S, then we would get a particular number of cycles to failure, and the number of cycles to failure, then at this point the applied S produces a certain number of cycles for failure. So at this instant, I'm going to call S sub F, which is the stress amplitude that leads to a particular number of cycles to failure. So to continue the terminology, we would have S sub F will produce a certain number of N, and these are the number of cycles to failure. So the consideration that we have is that we would like to characterize the relationship between S and N. So if I consider this relationship and look at the data, then the data will imply that I have S now sub F as a function of N, and N varies dramatically, so I have to use a log to the power 10 plot, meaning that I have one cycle here, and then I will have 10 cycles and 100 cycles and 1,000 cycles and 10,000 cycles and 100,000 cycles and then 1,000,000 cycles. Okay, and beyond that, if the test goes beyond 1,000,000 cycles, then we can think about the result as an infinite life. So it can continue on. So now my duty is to find a way to relate the SF to the corresponding number of cycles to failure. And as we learned from the previous lecture, we have two regimes. One is the low cycle regime, where ductility is important when the number of cycles is below 1,000. And then the other one is the high cycle regime, which is roughly between 1,000 cycles and 1,000,000 cycles. And then we have a third regime. If the number of cycles to failure is above 1,000,000, we can think about that as the infinite life regime. And therefore, we would think that we should have these simple method to represent the data. And this method is empirical because we want to use it quickly in design based on the available data. So for this method, I will represent it here simply as I have now a point on this. For one single cycle, I will define a point, and then for 1,000 cycle, I'll define another point, and for 1,000,000 cycles, I'll define a third point right here, and then above that, I don't need to define anything because I have an infinite number of cycles to failure. So this point is point A, this is point B, and this is point C. And now I just need to find the coordinates of these points. So if you think about it, then the coordinates of point A, I have failure in one single cycle. So the amplitude that would correspond to failure in one single cycle is the same as the ultimate strength of the material. And all materials, we can open up the data sheets and find the ultimate strength of the material. So that's the coordinates for that point is n equals 1 and sf is equal to s ultimate. So I'm going to write the coordinates for this point here next to it. So I have 1 comma SUT. And then for point B, which defines the end of the low cycle fatigue regime, the coordinates is by convention is 1,000 cycles, and then the strength corresponding to this point, which is this level of the strength, is a fraction of the ultimate. So I'm going to put it as a fraction of SUT. So it will be F times SUT. All right, so I introduced, so I'm going to write them on the side. This SUT is the key. Now I have a fraction of SUT that I should know, so I should know F. And then finally, the coordinates of point C will be 1,000,000 cycles, 10 to the 6, and not SUT anymore, but S endurance. So I have an endurance limit. So I need also the endurance limit. So the key is SUT, and then we'll find F, and then S endurance, we'll find it from a relationship. And if we're looking for an easy way out without doing much testing, the endurance limit is roughly half of the ultimate strength for steels, raw steels. So if you have cast steels, it will be less. If you have maybe cold work steels, it will be higher. And we have this correlation. So I will show you a figure that relates the endurance limit to the ultimate strength. So we're going to open up the manual, get the ultimate strength, use this correlation to get the endurance. If we don't find it, then we just divide S ultimate by 2 to get the endurance limit, and then we will find this factor that relates the amplitude at failure at 1,000 cycles to the ultimate strength. So I might just kind of try to show you here. This is, as you can see here, this is the endurance limit, and I'm going to call it SE prime. So prime is for the rotating beam. So this is the value of the endurance limit for the rotating beam specimen, and later we will modify that for the exact conditions. So it's basically half of the ultimate if the ultimate is less than 200 KSI, or is 100 KSI for anything larger than that. So this is kind of the recommendation that we have from ASME, as you can see here from the data. You can have it higher or lower depending on whether you have carbon steel, it will be lower. Wrought alloy steels would be higher because you have the more expensive steels. So now we have the endurance limit from the ultimate, and now there's a procedure in the book to find F, but the bottom line is that we have failure SF prime at 1000 cycles at that level of the fully reverse applied stress. So F times S ultimate. The value of F starts at 0.9 when the ultimate is 70 KSI, and then let's say for a good strong steel of 150 KSI, then I can find F to be 0.79, for example, 95, and therefore I can find that coordinate that I'm looking for. So if I go back to our discussion, then we essentially have at this point 3 coordinates, 3 points. Each one we have defined the coordinates from the underlying data. And then we wish to represent the data as a linear log plot, meaning that I'm going to put straight lines to connect these 3 points and look for equations for the straight lines. As we mentioned in the previous lecture, any equation, any linear equation on a linear log plot is equivalent to writing the relationship as a power relationship. So we're going to assume a power relationship for low cycle fatigue and another one similar for high cycle fatigue, and then find the constants in each one of the power relationships from the coordinates of these 3 points. So that's kind of my procedure here. So if I now connect the coordinates of these points, I will get a straight line here and another straight line here, and then a third straight line there, and that defines my regimes. I have now 3 regimes, and then I'm going to write here low cycle regime, high cycle. Okay, so then my next job is to find a way to write equations for these 2 lines. The equation for this line, I'm going to write it as SF. Obviously, at 1 cycle, the SF should be equal to SUT. So I'll write it as SUT times N raised to some power, B1. And B1, I can find it from the coordinate of point B. By substituting coordinates of point B into this relationship, it gives me B1, which is log F over 3 if you do the math. So we're done essentially with this relationship that I have now defined a relationship between SF and N for the low cycle regime, and I know how to find B1, and I know how to find this coefficient, which turned out to be S ultimate. Now the next we turn our attention to the high cycle regime, and we wish to write an equation for it, and the equation that we're going to write is going to be SF is equal to A times N to the power B, where A is when we can find the constants A and B when we substitute the coordinates of point B and point C into this assumed relationship. So the constant A, if you do the math, will turn out to be F times SUT square divided by SE, and the constant B, you'll find it to be minus 1/3 of log to the base 10 of f times SUT divided by SE. So this will be the solution that we'll find when we complete this substitution in the assumed relationship. And therefore, I have now a correlation, complete correlation, that describes the relationship between S and N that allows me to compute the number of cycles to failure. And as we know, above million, then if the S is below S endurance, then we have an infinite life, essentially. So this is basically the summary of how you can determine the equations for the relationship between S and N and use it in actual design. All right, so what's left? What's left is that I wanted to do two things. Number one, just get a couple examples on very simple calculations for lifetime based on the procedure that we've seen here. And then later on, maybe in the next segment, I will show you that the endurance limit and what you see is not what you get, because what you see in the endurance limit is based on a rotating beam specimen that is highly polished and under a very nice control. But in real life, then the surface conditions will be different, the size will be different, the environment will be different temperature and so forth. So there are a number of design factors that need to be accounted for to give us an extrapolation of the fatigue data that we obtain in the laboratory to the fatigue data that can be used in real practice. So let's just move on and see if we can get some examples here and review the data again. So as you can see here, this is a summary of what I've shown you before, but it shows actual data. Like you can see the data here, and then the actual the lines that we've drawn here are basically connecting the data together. I might want to add here a word about the graph, the representation. In fact, the representation, which is a power representation, A times n to the power b, must have a log to the base 10 of S and a log to the base 10 of n. As you can see here, it's a log. So I kind of misspoke that I was referring to a linear log, but it's a log. When you have a log representation here of the graphics, then you will get a power relationship and you get straight lines on the log plot. So that's the representation here. And then I wanted to take an example. So in this example, I have 1050 steel, and we wanted to estimate the rotating beam endurance limit at 10 to the 6 cycles. So before we go there, we can discuss it. If I want to represent the endurance limit, all what I have to do is find the ultimate strength and then multiply by the fatigue factor. That's about 1/2, and that gives me endurance limit. So if you can see here, this is the result as endurance prime meaning for rotating beam, before we do any additional factors that connect it to the actual practice, which we'll do later. So it's 45 kpsi. The second question is, what is the endurance strength of a polished rotating beam specimen corresponding to 10,000 cycles? So in order for me to go there, I know that now 10,000 cycles is greater than 10 to the power 3. So I have to use the equations for high cycle fatigue. And the equations for high cycle fatigue, we need to find this factor F, and the factor f for S ultimate 90, we can use the figure and find f equals 0.86. And once we do that, then we can find a and b. So if I just remind you again here for what is a and b, this is the value of a and this is the value b. With straightforward substitutions will give us the values of the two constants. A, note that has the units of KSI, and b is kind of dimensionless because the power, and therefore I got now a relationship that I can represent, and this relationship is given as you can see here, 133.1 times n to the minus, so it's a minus here because it's the slope is negative on the log-log plot, so again minus 0.0785. So this is easy to use because substitute for any n in here, then you get the corresponding SF prime, and in this case for 10,000 we got 64.6 KSI as the amplitude. So that in your mind, this is the value if you plot it here as a function of time. If you plot the stress as a function of time, the 64.6 is this amplitude. For problem point C is that what is the expected life under completely reversed stress of 55 KSI. So it's kind of the same equation but backwards. So we're given this and we want to find n, and we can rewrite it backwards and find the number of cycles to be 77,500 cycles. Okay, so I think at this point I'll stop, and in the next segment we will discuss the endurance limit modifying factors and then get in a few more examples.